All right, welcome back. We are going to today take a quick look at aldehydes and ketones after we first talk about the carbonyl group. We need to talk about that because aldehydes and ketones both have the carbonyl group. So first of all, what is it? It is an organic functional group composed of the carbon atom double bonded to the oxygen atom. And that oxygen, if you remember, it has two lone pair of electrons. And if you remember, oxygen is more electronegative. And that means we can consider it more nucleophilic, which means that it is nucleus loving, meaning proton loving. We designate that as having a partial negative charge. That's the lowercase delta. So we indicate that with a partial negative. The carbon, on the other hand, we say, because it has no lone pair of electrons on it, so we say it's more electropositive compared to oxygen. So we call it electrophilic. So it is electron loving. And we give it a partial positive charge. So on the carbonyl group, which is what this picture is, we can draw our two lone pair. I didn't do a very good job here. So this is one lone pair. This is another lone pair. And then we can show that up here we have our partial negative charge, and on our carbon we have our partial positive charge. All right, so again, this is called our carbonyl group. All right, the simplest carbonyl groups are the aldehydes and ketones, so that's what we're going to study right now. What are aldehydes? We'll start with that. They have a carbonyl group bonded just to a hydrogen, so they are at the end of a chain, and when you have just one carbon there, as in this picture, you really don't have a chain of carbons, you just have one carbon. That has a common name. Let me change the color here since I just used red. That is the common name for formaldehyde. You see the word aldehyde in it. Here, in this one, we have an R representing a carbon chain, and then on one side, you don't have an R, you have just the C to the OH. And then here you have AR representing an aromatic group. For example, benzene. If it were just simple plain old benzene, you would call this benzaldehyde. All right, and so remember that would be like that. All right, next on our agenda we have our ketones. A ketone is very similar, but just slightly different in that instead of having the hydrogen on the one side, you have another carbon chain. So you have a carbon chain on one side and a carbon chain on the other. So you have your R and then an R. Now, if it was just one carbon on one side and one carbon on the other, so that it was just CH3s on each side, that would be the simplest ketone, and that is acetone. That's the common name. That's the non-IUPAC name. If you had a carbon chain on one side and an aromatic, like again benzene, this is what it would look like. And then you could have a benzene or an aromatic, I should say, any aromatic, not just benzene. Could have one on each side. All right. Next, we're going to get into just the nomenclature today and do a few examples. So the rules for nomenclature probably are going to make sense because they follow closely our rules for organic nomenclature as well. The stem names are derived from the parent alkanes, so you're going to follow those same beginning names like, meth, eth, prop, bute, etc. Defined by the longest continuous chain, but the chain has to contain the functional group. For an aldehyde, you're going to drop the E and add Al. For a ketone, you're going to drop the E and you're going to add ONE. To indicate the position of a substituent on an aldehyde, the carbonyl carbon atom is always considered to be carbon 1. And since it's on the end, you don't need a number. Since it's on the end, it will always be carbon 1. However, on a ketone, you'll always number the chain so that it gives the lowest number possible. If it's in a cyclic ketone, you'll always call that carbon 1. So let's go ahead and practice these. Let's look at this first example. Let's break this down. In the first one, you have, since our carbonyl group here, and it's on the end, I should say, so I know I'm dealing with an aldehyde. We have 1, 2, 3, 4, 5. So we're dealing with pentane. We're going to drop the ending of E and change it to Al. We do have a branch, and it's a methyl branch. And that methyl is going to be on carbon 2. So when we put it all together, let's go ahead and name this 2-methyl pentanal. 2-methyl pentanal. Let's look at the next one. We have a carbonyl group. It's in the middle of the chain, so instead of an aldehyde, we have a ketone. Our carbon chain has 1, 2, 3, 4, 5 in it. Again, that is pentane. Because it is, a ketone, we drop the E and add ONE at the end. We have 2 branches now. Both of them methyl groups. So we have dimethyl. If we count left to right, the branches would be on 2 and 4. If we go right back to left, they'd be on 2 and 4. So either way, they are on 2 and 4. So we are going to call this 2, 4 dash dimethyl pentanone. All right, the next one, we have a cyclic compound. It is not benzene. It is not aromatic. It's just a plain old cyclic alkane. It's got 6 sides. So it's cyclic. So we know we're going to change that to cyclo. It is 6 sides, so that's hexane. But it does have a carbonyl group in the middle of it, so that's a ketone. So we change the ending to ONE. Because it's a cyclic structure, we just say that any of them could be carbon 1, so there's no numbering. So this becomes cyclohexanone. All right, now we're going to go and work backwards. We're going to draw this next one. We know Al means it's an aldehyde, which means our carbonyl group is at the end. It's at the end of 7 carbons. On carbon 3 we have an iodine, and on carbon 5 we have a bromine. So we have 7 carbons. 1, 2, 3, 4, 5, 6, 7. On carbon 7 we said we had a carbonyl group, or aldehyde. On carbon 3, now we have to call our aldehyde, that carbonyl group is carbon 1, 2, 3. So we have an iodine there. 1, 2, 3, 4, 5, we have the bromine. And again, make sure all of your carbons have 4 bonds. I'm going to change up your next one and make this a hydroxy. Just to give us a different one. So it ends in -one, so we know it's a ketone. Hept again, 7. Hydroxy means we have an OH. Bromo. So we have 7 carbons. 1, 2, 3, 4, 5, 6, 7. 2 heptanone means on carbon 2 we have our ketone. 4, 1, 2, 3, 4 mean we have a hydroxy, which means an OH group. And on carbon 5 we have a bromine. Again, make sure you go back and double check that everything has 4 bonds on every carbon. One last one, I'm going to add in 2-propenol. Just to make sure you see that if it's got an ENAL, that means it's got a double bond. It's an aldehyde. Propene, prop means 3. Al means it's got the aldehyde at the end. That's on carbon 1, so on carbon 2 it's got the double bond. And that would be 2-propenol. All right, there you go.